And hello, everybody. I hope hacking is going well. And so the goal for today's talk is to actually have like kind of overview of the different types of problems in machine learning, how they relate to oceanography problems, and how you can kind of approach maybe some of your own problems. And it's just kind of, a presentation. And let me figure out how to navigate. Okay, so these are the goals for today. Is basically we will discuss how to convert oceanography problems to machine learning problems. We will discuss different types of machine learning problems and how we differentiate them and what's common between them. We will discuss how to convert unstructured data sets so that they're ready for machine learning and the libraries that exist. And one of the most important topics is the evaluation. I'm going to say a few words about this. And one of the hot topics in general these days is deep learning. So I'll just kind of spend a little bit of time of saying, how deep learning is fitting, the general machine learning setup, and is there something different or not, and how that can help us. And so this is kind of the plan for now. It's going to be pretty high level in some sense, but on your own, what you can do is actually from last year, we actually have like a full tutorial on machine learning with Python, and it actually goes through a lot of different types of problems that you can do, and you can. Let me just show you quickly. So, okay, so here you can see that you kind of have some data loading, dimensionality reduction, classification, and deep learning. And this all is done with one data set of with whale calls and from hydrophones. But the goal of the tutorial is not specific to the whale call, it's pretty general. So the idea is that you can just kind of use this tutorial to take things out of it and kind of plug in your own data set, hopefully. So you can kind of spend your time by yourself doing that. Okay, so back to the presentation. And great. So there's a lot of discussion about what really machine learning is, and I'm not gonna get into the details like what really should be and what it shouldn't be, but I just kind of wanted for a second to relate to human learning and the types of human learning that exist and how that relate to the types of machine learning categories that exist. So one of the most typical ways of the way we learn is we kind of go to school and we have textbook, we read from the textbook, we get tested, we have a teacher who checks what we do, and we go back and we get the grade, and we kind of improve, we study more, and we keep on doing this over and over again. So this is supervised learning. But there is also unsupervised learning, where we have little children, they just look at some patterns, they don't have any instruction, but then they kind of discover something in those patterns. There's no teacher. And there is a third category of reinforcement learning, where you have like an agent, like a robot, which kind of goes and plays in some puzzle, and occasionally they get awarded, and based on that they change their actions. So these are actually the human learning ways. And the same thing applies to machine learning. It's just we kind of basically, our textbooks now are our data, which has some expert labels to help us out, and we do some training and some testing, and we keep on doing this again and again until we improve our what we have learned. So that is supervised learning. There's unsupervised learning. We just have data, we look at it, we discover patterns. And there is also reinforcement learning, which is actually very similar. You just have these agents that are kind of like, you know, like instead of like a kid playing a game, now you have a robot playing the game. And in oceanography, you can see that how your labels could be coming from just maybe some trolling or maybe some expert who annotated the data. But we can see how just looking at the second picture of the ocean, you know, without any labels, we see these patterns. And most probably we can run through some algorithm to see those patterns. And of course, we also have ROVs, and they kind of can navigate their own environment and figure out things on their own. So I think it's good to think about these categories, because when you start a new problem, one of the most important things, I think, is to identify really what kind of data and ground truth you have, because that can kind of maybe put you into one of these categories. And sometimes things get mixed, you know, some part is supervised, some part is unsupervised, that's fine. But I think identifying what is your ground truth is quite important. And if you don't have it, then maybe you go get it, or maybe you just look at unsupervised problems. So next, I want to kind of share this picture that some of you may have seen. It's quite popular. So this is kind of a graph that was created in 2013 about how to choose a machine learning algorithm. Like everybody wants this kind of guide, right? We just want somebody to tell us what we should do. So without getting into the details of like what the actual steps are, because as you know that this was kind of like just like I think like a fun way of kind of guiding people, but not really like, you know, you cannot really say what the right path is. But I think there's still a lot of value in this guide. But what's important is these categories that we have. So we have classification category, regression, clustering, and dimensionality reduction. And basically, if you kind of think a little bit about it, the upper two categories fall into what we call supervised learning, and the lower two categories fall into unsupervised learning. And all the methods that are inside are basically methods of the scikit-learn package, which is one of the most famous packages in machine learning in Python or in general. And basically, this package doesn't do reinforcement learning, so reinforcement learning is separate, but it still covers quite a lot of different methods. And you can kind of decide what to do based on that. So that's why I think why it is important is that when you try to solve a problem, you first have to understand what you're trying to do, like what kind of data you have, what kind of ground truth, but also what kind of problem you try to solve. And this was 2013. So we can ask, well, what about 2020? So apart from a lot of other things that have happened this year, there have been quite a lot of advances in the recent years in deep learning. And we can ask the question, well, are all these methods before, are they kind of irrelevant now or not? Did this graph change a lot? Well, actually, I think the graph more or less stays very similar. I kind of did a few changes. I tried to kind of modify it here and there. But okay, a lot of the old methods still are very relevant and we still use them every day. But one of the special things I can say is that I added these things which are called spatial or temporal. So if your data is spatial or temporal, you can do something special. So like in each category, you have this option. And usually that's where deep learning methods are actually helping, when your data is kind of has some correlation structure. But otherwise, you can still use the old methods. And if the new methods don't work, now the general advice is to get more data. That's what they tell everybody. So it's not like they came up with that much newer methods. It's more like they learned that with more data, we can do more. Okay, so these are the problems, and with one sentence, I'll just kind of define them. I think everybody has their own definition in their head, but regression is finding relationship between a set of variables and outcomes, like inputs and outputs. And we want to predict outputs on new variables. Classification is very similar. We just have the outputs are categories. So we want to predict some categories on new data. clustering is pretty clear. We group things into groups. And dimensionality reduction is a little bit more subtle, but the main idea is that we want to convert our data to something that's kind of of lower dimension, but also more informative than the raw data. And the boundaries are pretty loose in practice, but I think it still helps to make sure that you know, like, you're understanding what problem you're solving. And I've seen many times people start talking about their classification problem, but then their output is actually it's not a class. So it's important to think about. Okay, so let's look at one oceanography example from each of these categories, just kind of for the sake of seeing some examples. So first, regression. Sea surface interpolation actually can be formulated as a regression problem. And this is an example. Some of you are hacking actually on this problem this week, but this is an example from a recent paper in which we start with the Argo data, which is of course very sparse, and we want to interpolate spatially we want to make some predictions about new locations or new times using the information from the raw data. So, and in this case, actually in the paper, this is solved with Gaussian processes, and it's kind of one step above something like a standard linear regression, because it actually takes into account the temporal and the spatial structure. But in practice, this is actually a regression. You can think of it as a regression problem. Example of a classification problem is quality control. We can actually put that, we can formulate it as a classification problem. And let's say that we have some raw data of different parameters, different variables and different observations for them. And let's say that somebody came and annotated our data. Basically, they said it's good, bad, probably good, probably bad. So these become our labels. And one important thing in this case is to recognize that these labels are ordered. So it's a little bit less, again, it's not a traditional case because reality is never so traditional. So we can kind of should be careful because the categories, you know, maybe making mistake between good and probably good is not as equal as a mistake as good and bad, right? So we should take this into account, but we can still treat it as a classification problem. And in fact, in the paper which studied this problem, they actually approached it with fuzzy logic, which allow to have actually fuzzy boundaries. So in the sense that you can actually do something more than just a standard classification. You can actually allow for a little bit change in the boundaries. And if you actually want to use some solutions like that, there is also a package called TD associated with this paper, which is actually implementing this quality control method. Okay, so next, clustering. It is very common problem actually in gene analysis. People want to cluster the genes, and basically they look at the hierarchical structure of the relationship. So not only trying to put them into clusters, but also see which clusters are close to each other and which clusters are far away from each other. And this is one example. And lastly, one example of the dimensionality reduction is using principal component analysis to find patterns in sea surface temperature observations. And in this case, you actually get the El Nino by automatically without any supervised data. You actually get the patterns of the El Nino oscillation. So this is the actual oscillation, and these are the actual main modes that appear. And so in a sense, this is a very unsupervised way to discover something in a very large data set. Okay, so that's kind of what the methods, some popular methods are, but let's acknowledge that data in oceanography is actually very, very diverse, and basically data sets come in all kinds of shapes, sizes, and forms. And that's one of the challenges of sometimes applying those methods directly to oceanography problems. So in a typical machine learning tutorial, they tell you that your data set is ordered in this way. Each row is an observation and each column is a feature. And once you have that, you can go to scikit-learn and you can do a lot of things. But actually getting to this point is not a trivial problem, and you kind of have to spend time thinking about how to do that. And in practice, you know that we saw that our data sets are actually very multidimensional, and there is a lot of correlation in time, in space, in measurement protocols, and etc. So there is more to think about than just kind of getting a library and applying it to your data, which is not even in that format usually it's not even in that format. Okay, so basically that's why we need to do more steps into this process. And here's kind of a diagram of like supervised learning. I'll spend a little bit more time talking about supervised learning. And I think in the next talk, you will get a chance to discuss more some unsupervised methods. But like the first step is actually this feature extraction, and that actually applies both to supervised and unsupervised. But basically you have to actually put your data into some formats to be understood by the models and the algorithms. And once you have that, you can actually, you have some quality metric, which you can use to optimize the parameters in the model and find this kind of a function, which is either a classifier or regressor. And based on that, you can make some predictions and then kind of evaluate and then do it again and again. And you keep on kind of improving your methods. So this is kind of the typical process. And regarding the first step, let's look at an example. Let's look at an example of well-call data. So the raw data is kind of useless, but what people can do, for example, they have several options. One is to actually just create these features by hand using some sort of temporal and spectral properties of the signal. Another option is to filter the data set and create like a vector of the power spectrum. A third option is to create a 2D spectrogram and use that. And now you see that in the 2D spectrogram, you actually see the call, while in the raw data, you don't really see the call. So maybe that's a good feature. So somebody has to kind of decide what to do. And based on the features, you may decide what your methods are. So in the old days, people used to spend a lot of time creating these crafted features that fit their problem. Usually use your domain expertise to come up with them. And then one can apply like a simple method like a linear regression or a decision tree to actually use those features. And everything is very super interpretable. So it's kind of, in some sense, it helps doing science, but also there's only few problems that you can solve. So the machine learning approach today is a little bit different. It's usually saying leave the data as raw as possible, and let's hope the algorithm will figure out those features. And then we can also use more complex problems to find those nonlinear relationships, and we don't have to come up with our own nonlinear features and so on. So that's all great. But by allowing to have more dimensions and more flexibility in the model, we kind of increase the variance of the problem. So in the first case, having a very specific features and a very basic model, we have very high bias, right? We're biased toward what our assumptions are. In the second case, we have a lot of variance. And it's not like one can win. So because there is this principle of bias variance trade-off. So basically neither one is the right solution. You have to find the optimal solution. And in practice, the reason is because the prediction error is a sum of the variance and the bias and some other error. So in a sense, you make one big, like that doesn't kind of sooner or later, like you may be kind of making the other one small. So, and in this picture, we can kind of look at it that basically, if we look at the error, sooner or later, when we increase the model complexity, this error starts to go up. So also, like, you know, like when the model is super simple, the error is high. But then there is like optimal kind of like middle ground where you can have good prediction error, and that's kind of like, that's sort of your bias is kind of like decent, and your variance is sort of decent in some sense. So you kind of are shooting for this middle ground. And if you are having too complex model, what can happen is you're overfitting. Basically, you have too many parameters to fit, and it's very easy to do it, but it's not going to work on the next data set. Or if you take a too simple model, you are underfitting. So you basically, your model is not flexible enough. So that's kind of the main principle that we encounter in machine learning, and that applies to any domain. It doesn't matter whether it's oceanography or any other domain. So it's good to think about it, because it makes us decide these models. Okay, so then the next thing is to, in this diagram, you know, when we evaluate the error, we have to decide, we have to be very careful because of this overfitting danger. We have to be very careful how we evaluate our model. And the standard practice is actually to split things into, to have a testing set that we put apart and we don't touch it. So we're just gonna use it in the end when we finally evaluate our model. And then we have another extra validation set that we can use to tune parameters. And that we can look at it many times so that we improve our methods. But it's important to remember that the testing one, you should not look like 10 times at it and keep on improving your model. If you start doing that, this means that you already already having a validation set, not a testing set. Okay, so, and a further like improvement can be like to do cross validation, which in that case you have several validation sets. Okay, so, and then one thing about evaluation metrics is that if you just have a statement like this, our algorithm achieved accuracy of 99%, that means nothing to me. I'll have a lot of questions to ask you, and it also means nothing for the science because I don't understand what you're doing. So I think it's important to explain really what that means. For example, in terms of the whale problem, I want to be told what it means in terms of like detecting calls. I also want to see like different types of errors, like accuracy just involves certain types of errors, and confusion matrix is a way to look at all possible errors that you have made in a classification. And that can kind of tell us a lot about how you're going to use this in practice. Like, for example, your methods, in this case, it turns out that there's two more things that are important, precision and recall. And turns out that we're basically, we're kind of having we're retrieving very few of the actual calls. So that's kind of tricky. So basically we're like, we're missing a lot of the calls. So that's important for the science. So there's a few more questions to ask, like, what if I just predict no? Is this better? Like the accuracy is 78, that's like a good number. But actually that may not be good if really like, basically 30%, if only 20% of the calls are, of the observations are calls. So that's why I kind of want to compare to yes and no classifier. I want to compare to a random guess. I want to know how you decided on your threshold. By default, scikit-learn says the threshold to 0.5. And maybe changing that threshold, I can actually achieve different results. I want to also know whether it's going to work on a new site, a new ship, new season. So I really want to understand how you design your sets, your testing sets, so that I understand whether if I apply it to a new data set, whether it's going to work or not. Like maybe it works only when you do this on Mondays or something like that. So that's kind of tricky. Okay, so I'll say briefly that regarding algorithms, there are many algorithms, but the main thing is that you actually have to you have to really compare. There's no way to say whether the method's going to work or not. But in general, I recommend trying one linear method and one non-linear method, just so that you see the range of performance. But you actually have to evaluate and see what works. I don't have a lot of time for the machine learning, for the deep learning part, but I can briefly say a few words. So basically, deep learning is just doing machine learning with neural networks. Example of a simple neural network is actually logistic regression, one method that you may have seen in your statistics class. And you can have a lot of them nested. But actually, these type of networks are not useful. What I said before is that deep learning can be useful specifically for temporal and spatial data, and that doesn't get achieved just by a fully connected network. So then there's like architectures that actually help way more for spatial and temporal data. So one example of this is convolutional neural networks, which are basically capturing some of the spatial information or kind of local information, or you can have like a sequence network, which kind of help with the temporal information. So when you look at kind of like examples, keep this in mind, that not just doing neural networks on a general problem makes no sense. You have to have a reason for that. I have extra slides, but I kind of don't want to go over time. I have a little bit more details of just examples of using convolutional neural networks in oceanography examples, and there are many of them. And basically, one can also go beyond like standard problems, like the 4 problems that I mentioned. And this kind of goes more into the area of computer vision, where you can have like actually detection of objects and segmentation and so on. Also,
hey,
I'll just...
Valentina, since we are at 31 minutes after the hour, maybe if this or the next slide is a good stopping point for you, we could stop for questions and brief questions.
Yeah, I'll say that also, like for those who work with numerical methods, they also can use that for speeding up their numerical analysis, which is a totally different application. I think this is a good slide to stop at, because it also to remind us that we have all these different methods, and they increase we start to lose the interpretability. So we have to always go back and look at different ways to understand what we're really doing. And here are some hints for you to what kind of look for at the different methods. I'll stop here with the actual links to the technical stuff of how to actually do this stuff. So feel free to ask any questions.
So I'll turn it over to Nick and Allison, who are the Slack moderators who've been monitoring the questions, and they're the ones who will ask the questions.
Thanks, Emilio. Yeah, that was really great, Valentina. I really thought that was a great overview. I think most of the questions got answered on Slack, but I think the only one, which is a good question, is what do you think about the explainability versus predictability trade-off?
I think it depends what kind of problems you're trying to solve, and it really depends on your objectives. I think that's why I'm kind of very strong about comparing a lot of things, because basically even those features like that we have here, they actually that you can have different methods to kind of get a sense of like what is important. So one should be very careful about how they interpret them, especially in science. Like just because you have a variable called variable importance in scikit-learn, does that really mean that your variable is important? And they're very tricky things, and you can actually, these this can be tested also on new data sets. So basically you should test your features importance also on new data, so that it's not like just it's important for that data set that you like your training data. So yeah, I think in general, there are cases where for the application, if it works, that's fine that we don't understand why. But most probably by works, just because it worked on a small data set, most probably that doesn't mean that it works. If it really works on a lot of data, then most probably sooner or later we'll understand why it works. So in a sense, if it really works, we'll understand why it works. But if it just works because you applied a very complex method on a 10 variable problem, you know, like it may not be interpretable at that point.